We have spent some time now looking at graph problems where we saw questions which were of a true and false variety. For example, at one point we looked at graph colorings and asked questions like, does this graph have a 3 coloring, or a 4 coloring, or 5 coloring? At another point, we looked at Euler path and asked, does this graph have an Euler path? We also looked at Hamilton paths and asked, does this graph have a Hamilton path? And in many cases, there were easy ways to answer it. The Euler path case was particularly easy. It said if the graph is connected and there are 0 or 2 odd degree vertices, then you can pass over every edge without repeating any. When we looked at graph coloring, we didn't have a very clever way to answer it. We just sort of tried to color and it seemed to work. When we looked at Hamilton path problems, those are probably the hardest of them all. With small changes, a graph might go from having a Hamilton path to having none. It turns out that graph coloring and Hamilton path problems are both very important in what's called complexity theory. So I'm going to give here a very brief introduction to complexity theory, because I think this is a really fascinating subject that touches on a lot of math. It feels like a computer science problem, but it explains to us why many math problems don't seem to have clever answers. So let's start with some definitions. So suppose we're considering a true-false question, like, does this graph have a 3 coloring? Does this graph have an Eulerian path? We say that this question has polynomial time complexity if it is possible to answer the question, yes or no, in a number of steps polynomial in the problem size. So when we're looking at graphs, the problem size is usually defined as the number of vertices. When we're looking at some problems with factoring, it's the bit size of the numbers. How many bits does it take to store that number in a computer? So many problems you look at have easy algorithms. You do some process, at the end you find out if it can be done efficiently. Now let's look at something which is a little bit strange. We say that a problem has NP, time complexity. This means non-deterministic polynomial. If yes question answers with a yes answer, always have a proof that can be checked in time, polynomial in the problem size n. So this means it might be hard to find an answer to this question, but it's easy to check it. For example, we talked about coloring graphs. If a graph is 3 colorable and someone gives you the coloring, you can check it easily. Just look at every point, make sure that adjacent points don't have the same color, you're done. So it might be hard to find the 3 coloring, but it's easy to check it if someone else finds it for you. Now let's go one step further. A problem is said to be NP complete if every problem in NP can be converted to a case of this problem. And there's another restriction which can be converted in a number of steps polynomial in the problem size. What that means is, give me a problem about graph coloring. I will convert it to an NP complete problem pretty quickly, polynomial time. Well, NP complete turns out to be really hard. It can be shown that there are these problems that are NP complete, and that means that if you can solve one of these efficiently, you can solve every single NP problem efficiently, because every NP problem can be turned into this NP complete problem, and then it can be solved efficiently. Efficiently is defined as polynomial. That's a very vague idea. A 100th power is efficient in this sense. Well, it is widely believed that NP-complete problems cannot be solved efficiently. In fact, it turns out that if I can solve an NP-complete problem efficiently, then current methods of securing your online banking account can be hacked quickly. The method Bitcoin can also be hacked quickly, meaning I can go out and steal everybody's Bitcoin if I wanted to. So this is probably hard. In fact, if you can find a way to do this efficiently, not only could you become a mastermind criminal, but there's also $1 million prize. And the $1 million prize can be won also by showing it's impossible. So if you can show NP-complete problems can't be done efficiently or can, you get $1 million. So let me give you a few examples of this. Let's start with the top problem. Is 17 a factor of 100? This is a true-false question. How would you solve this? Well, that's easy. Just do long division. $100 divided by 17. Do some work like in high school, before high school, and you'll find it has a remainder. The remainder will be non-zero. So no, 17 is not a factor of 100. This is something you can do quickly. How about this next question? Is 661,643 composite? That's hard. You know some methods to do it. You could try, is 2 a factor, is 3 a factor, is 5 a factor, is 7 a factor? It's going to get really slow checking every possible factor. In fact, if you go and use the prime number theorem, you can find out that the number of potential prime factors is much larger than the bit size of this number. So that would mean, well, it's much larger in the sense that it's not polynomial. So checking every possible prime factor is not a polynomial time algorithm for determining if this is composite. So it seems to be hard. Some time ago, some mathematicians in India figured out a clever way to answer this that was efficient in the polynomial sense, but it's not at all obvious. It took decades for people to find that. So let's instead talk about NP time complexity. You recall that NP means maybe you can't find the answer easily, but you can check it. Well, I'm going to tell you that 541 is a factor. Okay, don't need to know how I found it, but we know from the top here that if somebody gives you a factor, you can just do long division and check that it works. So all you need to do is take 661,643, do long division, and you'll find the remainder is 0. So this shows us that answering questions about composite numbers is in NP. Like I mentioned, there is a clever way of doing this without going to NP, but at least it is in NP. Let's ask another question. Does this graph have a 3 coloring? I haven't given you a graph, just does a graph. Well, this is very surprising, but this is an NP complete question. So if you come up with an algorithm that you think can answer this, meaning you think you can look at the graph and always find out if the answer is yes, then that algorithm can solve an NP complete problem. As I discussed earlier, if you can solve an NP complete problem, you can steal all the money from my bank account. You can get $1 million prize. There's a lot of things on the line there. Geniuses have looked at this. Nobody knows how to do it. So this is probably impossible to do efficiently. How about this next question? Does a graph have a Hamilton path? That means you can walk around and visit all the vertices exactly once. This is also NP complete. Little surprising, but if you think back to answering these questions, Hamilton path was actually pretty tricky. Making minor changes to a graph could make it go from having a Hamilton path to not having one. So this is also NP complete. Again, that means if you can come up with a way of quickly determining if there's a Hamilton path, then you can steal all my money. Alas for you, I'm not rich, but you could also win $1 million prize. That's better than stealing my money. So there's a whole theory here. And if you're interested in this more, I would strongly encourage you to look into complexity theory. It's a fascinating topic. There's a lot of math problems, like the Hamilton path one, where there doesn't seem to be a good way of determining whether these paths exist quickly. And complexity theory tells us that the reason we can't seem to do it easily is because this is an NP complete problem. And lots of problems can be solved if you can do it. So many problems that nobody thinks you can actually do it. So pretty interesting. Also interesting that we don't actually know the answer. Like I said, if you can figure out how to do this efficiently, or if you can figure out how to prove it can't be done efficiently, you win $1 million prize.